All right, I need you guys to do me a favor for a minute. I wouldn't have done this except it was proven to me in first period that I kind of need to. So we're going to be talking about some old information and some new information today. I'm going to start with the old information because I think you might need a little bit of a refresher. I want you to imagine for just a moment I have like just a sheet of ice or something that is big enough where a person could stand on it, and it's floating on some kind of frictionless surface. And perhaps the shore is right here. And this, let's go with a 60 kilogram person is gonna run and jump onto this 100 kilogram floating raft, okay? That suggests that in a moment there will be a person standing on this floating raft. What's the speed of the person in the raft after they jump onto it? You guys know things, so you should be able to tell me. I'll give you 60 seconds, and I'll just pick one of you. But this is a type of collision that we should be familiar with, called a perfectly inelastic collision. This is a perfectly inelastic collision, and that means that the momentum before the collision has to be equal to the momentum after the collision. There are no external forces that act on the system. So because of that, if we look at the momentum before, 60 times 3, the raft has no momentum itself because it's stationary. After the collision, both objects have the same velocity. We can treat them as a single object with a single inertia. And so our velocity is going to be equal to 9/8 or 1.125 meters per second. Makes perfect sense. Now, the example we did here, but is there a top-down view of this problem? Meaning we're looking down on the raft. Let's say the raft is circular like that. The person was running here and jumped on. Still the same kind of problem, right? You know, if the shoreline ends here, and they jump onto the raft, then can we agree that in the same way that we just described it a moment ago, the person will be standing on the raft, and they and the raft will be traveling this way? Any problem with that? We tend to draw it from the sides, but it'd be the same kind of thing, wouldn't it? But what if they were running, say, over here? This would change the problem a little bit, wouldn't it? You know, they would land maybe here. This doesn't change their momentum. The rules for momentum are still the same. But I kind of feel like if they jumped at the edge like this, that the thing might be spinning a little bit too. Does that make sense to all of you? No, it's still going to be moving away from the shoreline. That's no different. The linear momentum of this system is not connected directly to the angular momentum of the system in the same way that the linear momentum before the collision is equal to the linear momentum after the collision. That problem is still the same problem. But I think most of us have this kind of innate idea that if they jumped in this manner, it would probably also cause the system to rotate. And you should have some words that you could associate with this that might explain why it begins to rotate. I mean, when they land, maybe strike this point right here and push on it and apply a force here. That force likely causes an acceleration, which is why the raft will begin moving. But can you also imagine that force also probably causes a torque? And because it causes a torque, it'll probably cause the system to start spinning. So I want to isolate this problem, meaning I want to focus on the rotational part of this problem, since that's the unit we're really talking about right now. So instead of making this a floating raft, let's say it's a merry-go-round, and it has a fixed axis of rotation at the center. Now this is different. This is not a sheet of ice on a frictionless surface. This object has a fixed axis of rotation and is attached to the ground. Everybody understand that there's a difference here. In the prior case, the object was free to move. But in this case, when they land on the merry-go-round, although they will apply a force to the merry-go-round here, the merry-go-round's not going to just start sliding across the ground this way, will it? You guys have seen merry-go-rounds before. They don't do that, right? They stay in place. That's because on a merry-go-round, if you apply a force here, if the merry-go-round began to slide, the ground would apply a force here to keep it in place. This is an external force from the ground on the merry-go-round. And because this external force acts on the merry-go-round, it acts to change the momentum of the system. Now, I'm trying to be very careful with my vocabulary here. You should be listening very cautiously. There's two kinds of momentum. There's translational and there's rotational. We know that to change translational momentum, we have to apply an impulse, an unbalanced force for some period of time. An unbalanced force. For the merry-go-round, we're applying a force to the merry-go-round, but there's a force from the ground that holds the merry-go-round in place, so the net force on the merry-go-round is zero, because the merry-go-round isn't going to slide across the ground's going to hold it in place. But that force is applied at the center, at the axis of rotation. If the person jumps on the merry-go-round, I think it's reasonable to assume that there will be an unbalanced torque. Their force is applied at the edge, but the force from the ground is applied at the axis of rotation. So the force from the ground can't apply a torque because it's applied at the axis of rotation. I think that's probably important. This is why the merry-go-round will spin when the kid jumps on it, but not slide across the ground. The ground applies a force, but doesn't apply a torque. Your ability to explain this, I think, is important. Now, this means that for whatever amount of time this torque is applied, there's going to be a change in angular momentum of the merry-go-round. So the kid jumps on the merry-go-round starts spinning. Now, hear me out for just a minute, because I got a few of you that are falling asleep because it's Monday. And I'm going to need you to be more with it for this. You want to spin a merry-go-round, what, you got two different ways? You can stand around the outside of it and push on it, right? You are on the outside, you are fixed in space, therefore you, being external to the system, can apply leverage against the merry-go-round by applying forces, hopefully in all the same direction to get it to spin. Pretty straightforward way of spinning it, right? Remember, this is an external force because you're standing on the ground and you're rooted in place because of friction between the ground and you. This allows you to apply this external torque to the merry-go-round. Of course, anybody who's been on a merry-go-round knows that there's other ways to get it to spin. If you want to enjoy the ride, you might run around the merry-go-round while holding on to it, right? That'd be similar too, wouldn't it? You'd still be able to apply a force, and then maybe you jump on after it gets spinning. And that's why kids do that. Sometimes kids believe that they could stand on the merry-go-round and kind of give it a push, but that's much harder to do. Have you ever tried that? Anybody ever been on a merry-go-round? This is harder to do, isn't it? Doesn't seem as effective. You can't get as much leverage. And that's because you're not standing on the ground. You get more leverage when you put all of your weight on the ground. This other method of having somebody run towards the merry-go-round so that they run right at the edge and then jump on at the edge. This would also work. And I think you guys are aware it probably would work. They would be on the merry-go-round, and the merry-go-round and they would now have angular momentum. This is a perfectly inelastic collision. Just like in this case, the system doesn't have linear momentum after the collision. It only has angular momentum after the collision. The trouble with this is the kid that's running before he strikes the merry-go-round. How do we quantify his angular momentum? He's running in a straight line. In fact, it's hard to even imagine that he has angular momentum because he doesn't appear to be spinning. Physics has determined a way of dealing with this problem and using it to be a way to solve this. And so they have created a method of measuring angular momentum for what's called a point particle traveling in a straight line. This is the angular momentum for a point particle traveling in a straight line. To understand this, I'll remind you that the pivot point is here. The first thing your notes probably should have in it is that for angular momentum, we have to have a unified pivot point for the objects that we're observing. We've been doing that already, but I haven't said it like that because there hasn't been more than one object, or it's been obvious that there's a pivot point that all the objects share. But now I'm enforcing it. I'm saying in order for us to deal with a conservation problem using angular momentum, we need a unified pivot point that all objects share. I'm going to make it the merry-go-round because it's what's going to be spinning at the end of the problem. Because it's going to have a clear angular speed about that point, I'm going to use the pivot point that's fixed on the merry-go-round as my fixed pivot point. So now I want to focus on the kid. Since everything is relative to the pivot point, imagine a line drawn from the pivot point to the kid. Now, if you're standing on the pivot point and you watch this kid run by, wouldn't your head have to spin as you watch the kid run by? Can you guys imagine that? As they're running by, your head would have to pivot in order to see them run past the merry-go-round. You guys understand what I'm saying, right? Now, I want you to just watch. If we're talking about that red line is clearly going around as it traces this person's path. Can you agree with that? Just like so. So we define angular momentum for a point object by first drawing a vector from the pivot point to the object. We label that vector R. Of course we do. We label everything R. That defines an angle now between R and the velocity. This part's important. And in physics, we state that the angular momentum for a point particle, you'll notice I'm using a lowercase script L. This is to differentiate a point particle's moment of inertia from a physical object that spins. We used a capital L for a physical object that spins. We use a lowercase script L for a point particle. It's in your notes this way. It's in your equation sheet this way. We defined the angular momentum as r times the linear momentum times the angle between the two. Okay, we define L, the angular momentum, as r times the linear momentum times the angle between the two. So, r mv, sine of the angle. That's how it's defined. And we state that the object has angular momentum, and we should say it fully, relative to the middle of the merry-go-round. This angular momentum is only relevant because we know the kid's going to jump on the ride. If he doesn't jump on the ride, his angular momentum is meaningless. So remember, this construct is all about being able to solve and predict future events. So the creation of this idea of angular momentum is to find a way to deal with the kid's motion about the axis of rotation. That's why we have this. But there's lots of points in space. So his angular momentum is only relevant because he's going to jump on the merry-go-round. You guys understand what I'm saying here? He doesn't just have angular momentum because he's running. He has angular momentum because we're going to try and figure out what happens to the merry-go-round. So his angular momentum is only relevant with respect to the merry-go-round. Otherwise, he has no angular momentum. If there's no merry-go-round in this problem and he never jumps on one, he has no angular momentum. This only has meaning because there's this value r that connects him to the pivot point. So random objects in space that have momentum don't have angular momentum. They have angular momentum with respect to a situation in which they may rotate later. I've said this 4 different ways. I'm not trying to just use up the extra time and use up my, the space in the room. This angular momentum is only relevant because there's going to be a future situation in which they are going to spin. Otherwise, any point in space would be a point. It doesn't make any sense. This value for r is only relevant because they're going to jump on the merry-go-round. And please, there's future problems, right? There's the bat hitting a baseball. That is an angular momentum problem where the ball has angular momentum relative to the batter after the batter strikes the ball. It is a collision between the bat and the ball. And the bat is rotating. It is a rod rotated about its end. So there are lots of circumstances in which this kind of angular momentum has real-world evaluations. Golfers, too. The club striking the ball, that is a clear rotational object, the golf club. The ball's angular momentum after it's been struck is relative to the golfer's shoulders. Everybody following this okay? All right. Now, there are a few of you in the room who are pretty sharp, and you might recognize that this seems to be a bit of a problem. If you don't understand where I'm going with this, let's reorder this for just a minute and write this as r sine phi times mv. I'm reordering it on purpose because I want you to imagine a few seconds into the future where the kid is now right here. Is it clear to you that after they've moved a little bit, r's different? And at the same time, the angle's different? R's getting smaller while the angle is getting bigger. Is their momentum changing as they're running? Now, it might be hard to see, but this R is getting smaller in the same proportion as sine of the angle is getting bigger. If you don't believe me, I can prove it. So I'm going to take just a moment to prove this to you. It's pretty easy to prove, but it also will be the real way we'll solve these problems, so I'd like you to see it. To prove it, I'm just going to draw a triangle, because I kind of see a triangle here. Do you guys see this triangle? I kind of see this triangle. This is a right triangle, and this is the original angle for phi. Now, sine of phi would be the opposite side divided by the hypotenuse. This is the hypotenuse. This is the opposite side. Everybody see that okay? So the opposite side is r sine phi. You guys see that? This is very important that you do, because I'm going to draw another triangle to where the kid will be in just a few minutes. Do you see that the opposite side is still the same size for this triangle too? So as long as the kid runs along that line, R is getting smaller in the same proportion that the angle is getting bigger. But this is the important part. This is the part that I really want you to write down. This is the radius of the ride. It's also called R of closest approach. In these problems, generally, we're not told where the kid starts because it doesn't matter. If the kid jumps on at the edge of the ride, we will almost always use R of closest approach, which we write R perpendicular MV. All right. I know that's the end.